Hello, and welcome to your final lesson on numbers as part of the higher mathematics course. In this final lesson, we're going to take a look at prime numbers. So you might already be familiar with what they are. Um, if not, we're going to talk about that. How do we find them? What are their uses? Then also how they are used in constructing other numbers in terms of prime factorization. And then we're going to look at a couple of common uses, which is finding what's known as the highest common factor and lowest common multiple. And we'll see that they have many um, uses in the real world if you decide to, go down a technical field with your careers. So let's first of all look at just what primes are and how to find them. So an example of a prime number would be a number like 13. And how we can tell that is from when we try to factorize it. And by factorizing, I mean finding two numbers that multiply to get 13. We can only find the trivial case, which is 1 and 13, which is true for all numbers. Every number, is going to be divisible by 1 in itself. Um, when we look at a non-prime number, like say 15, you see how we can divide it up into two numbers that multiply to create 15 that are not equal to 1 and 15. So these are what are known as proper divisors. Um, and we can go one step further, we say a number like 30, if we break that down into 2 times 15, in this case, we've got two numbers, unlike the 3 and 5, which are prime numbers in themselves. We see here 15, we know isn't a prime number. So this is a factorization, but this is not what's known as the prime factorization. We can look more detail into this in a moment. If we break this down into its prime factors, it would be something like this, 2 times 3 times 5. And you see you can't break that down any further. So yeah, take a look at this grid here. So this is a grid of all prime numbers up to 100. And you can see there's not so much of an obvious pattern to it. We'll take a look in a sec. There is a pattern uh, if you look hard enough. Um, so let's take a number like 16, and we're trying to deduce how can we find out whether or not a number is prime. So how do we find the numbers in this grid? The ones that are marked red. How can we actually work out that they're prime? So we take an example like 16. Um, and what we want to do is we want to try and find out in the fastest way. I mean, you don't want to have to check every single number up to 16 and see if it's divisible by that number. Or sometimes people will go up, check all numbers up to half that number. So in this case, we check 1 to 8, but there's actually faster ways of doing it. And by observing how factors come together. So say with 16, we can split that up into 2 times 8. So we start off with like the first factor of 16, which is 2, and its counterpart is 8, which makes up 16. You look at the next factor, which is 4, and its counterpart is also 4, which makes up 16. And then you continue to the next factor, which is 8, and its counterpart is then 2. You might notice here there's somewhat of a symmetry. You have the square root of that number, which is 4, which is, that number times by itself is then going to produce, your number that you're looking at. Like in this case, 4 times 4 gets 16. And then on either side, you're essentially going to get the same factors. So we see on the left-hand side, we look at, whether or not it's divisible by 2, and we see it is. And then on the other side, you're going to get, you try and divide by 8, you're going to get the remainder of 2. And so we actually don't have to check both sides, because if there's nothing, say if it wasn't divisible by 2, then there would be nothing else on the other side of the square root that would also be divisible by either, because it would have to be symmetrical. There'd have to be something on both sides, like in this case, 2 and 8, which are on either side of the square root. If you didn't have the 8, then you'd have nothing to multiply the 2 by to get to 16. So we can actually use that, which is a much faster way of working out whether or not we have primes. We don't have to check all numbers under the number. We only have to check numbers up to the square root of that number, because if there's no divisors on that side, there won't be any divisors on the other side of the square root either. And so that saves us a lot of time, because the square root, that drastically reduces how many numbers we have to check. And we can even go one step further than that. Like we don't have to check all numbers up to the square root of that number. We can just check the prime numbers up to the square root of that number. So that's why it's good to be familiar with some of your smaller primes. Like say in this table, like your primes up to say 29, you should be, quite familiar and be able to, rattle off that sequence of primes quite quickly and easily. Because then, yeah, the reason why we only have to check prime numbers, because say if I want to check whether or not a number is divisible by 6, if I've already checked that it's not divisible by 2 and it's not divisible by 3, then it can't be divisible by 6 because 6 is made up of 2 times 3. If it's not divisible by 2 and 3, then it can't be divisible by 6. And so that's why we only have to check the primes. So bottom line is we only have to check the primes up to the square root of a number to determine whether or not that number is a prime. So maybe this will be clearer with an example. So say if we take number 589, quite a large number, you won't want to check all the numbers less than 589. So what we do is we find the square root of that, which comes out to about 24.3. So we only have to check the primes up to 24. And if I put that down as a list, you see it's basically just these numbers. So of all the numbers um, under 589, these are the only ones we have to check. And if it's not divisible by any of these numbers, it's not going to be divisible by any number other than 1 in itself, which makes it prime. So using our divisibility laws that we've seen before, you can see this is not going to be divisible by 2 because the last digit is not divisible by 2. It's not going to be divisible by 3 because the digits add up to, uh, what is that, 22, which is not divisible by 3. So therefore the whole number is not divisible by 3. The last digit is not a 5 or a 0. So it's not going to be divisible by 5. So there's a few like that we can just eliminate straight off the bat. The remaining ones, you might have to just use a calculator and check each one. And as we go through each one, we can see the only one it's actually divisible by is 19. 19 times 31 produces 589. So we know this one is not prime, but if you manage to eliminate every one off this list, then it would be prime. So there we go. That's a fast way, the fastest way really that we can check whether or not a number is prime. So, um, is a little extra, like in terms of the pattern I mentioned in prime numbers. Like this is something you don't necessarily need to know for your GCSEs, but something I find quite interesting is that there's one way you can see a pattern. If you imagine plotting all the primes against themselves as coordinates, like 2, 2, 3, 3, 5, 5, 7, 7, like this. We haven't looked at coordinates yet, but if you are familiar with coordinates and you plot all these points, maybe you want to come back to this when we do look at coordinates. You see this kind of pattern forms when you plot them all, like this spiral like pattern. And when you zoom out much further, you start to see these lines, radial lines coming out from the center. So there are some interesting patterns, and why these occur is a little bit tricky to unpack, but there are some really good videos on YouTube I would recommend taking a look at to see why these primes have this pattern. But like I said, that's just more for your own interest. That's not part of the GCSE course. Let's take a look at prime factorization. This is something you absolutely need to know how to do well. So say if we have a number like 630, the prime factorization would look something like this, where you see 2, 3, 5, 7. These are all your prime numbers. So you've basically broken this number down into factors and then broken those factors down into their factors. And you keep doing that until you're left with numbers that you can't break down any further. Those are your primes. Primes can't be broken down any further. And so this is basically 2 times 3 times 3 again, hence the 3 squared, times 5 times 7. And that gets you to 630. And what we want to know is, okay, how would you find that? Say, we don't know what that is. We're just given the number 630 and we want to find out what that uh, factorization is. Now, what we do is start trying to work out what prime factors it has, because just by looking at a number, we can already determine a few. Just again, using those divisibility laws, we can see this is divisible by 10. Therefore, that means it's still so divisible by 2 and 5, because that's 0 there. So we get factors 2 and 5. And we can also see that it's divisible by 3, because you've got 6 plus 3 plus 0 is 9. That's divisible by 3, so we've got a factor of 3 there as well. And that's a good start because, okay, right, we can see this is going to have 2 times 3 times 5 times something else. We don't know what something else is. Well, what we could do is divide these factors out, like take 630 and divide it by 2, 3, and 5, and what's left over is 21. Well, we've reduced the number down quite small now, 21. You take a look at that, you can see what two primes are going to make up 21, or two or more. It could be more, but in this case it's two. Comes out to 3 and 7. And so there we go. We've now broken this down all the way into its prime factors, and those two threes we bring together to be 3 squared. That's the type. This is the typical convention how you do it. You use your indices laws like that, and you do them in order. So 2, 3, 5, 7. Right. So that's one way you could do it, just using divisibility laws, or something that can certainly help. Um, the more sort of formal way we do it is using something known as a tree diagram. So we start with our number of 630 there, and then we try and think of a number, the biggest number that divides this number. So I can see that 63 is going to be divisible by 3. And so therefore 630 here, I can see would be divisible by 30. So that's one factor. And then 630 divided by 30 will then get you your 21. So these two factors, 30 times 21 gets you your 630. And then we can start breaking it down from here. So 30, well, the 21 we've already seen is 3 times 7. The 30 we can split up into 6 times 5. Now that 6 can also be split up into 2 times 3. And these numbers at the end of these branches of the tree diagram, this is what makes up your prime factorization. So you've got 2 times 3 again, times 5, times 7. So this is more of a formal way of working it out. And if we try again for another number, like a common thing I do see is people, you would pick quite small numbers. So you might look at, say, you see that it's divisible by 2. So you split it into 2 and 252. 252 is still quite a big number. Ideally, you want to try and find the largest number you can that you can divide it by, so that you get two numbers that are of relatively the same size. So like I'll show you here, it produces a bit of a problem because you find you can divide this by 2 again, and you can divide it by 2 again, and then you get by 3, and then by 7 and 3, like that at the end. And you see it's quite a long and unbalanced tree diagram here. If we go back to the start and instead try and think of the biggest number you can, and it doesn't even have to be that big. I could look at 504. Now, multiples of 100 are always going to be divisible by 4 because 100 is divisible by 4. You might remember that from, say, when we was doing fractions and percentages and things like that. So 500 is divisible by 4, and so therefore 504 will be divisible by 4. So I can see there's a factor of 4 here. Also, by adding up the digits, 504 comes up to 9, which is divisible by 3. So I see there's a factor of 3 as well. So 3 times 4, it's going to have a factor of 12. And so if I split that up into 12, the other component would be 42. 42 times 12 gets you 504. And so we see straight away we can get to two much smaller numbers and it's more balanced. So 42 we can split up into 6 times 7. 6 goes into 3 times 2. Similarly, 12 can be split up into 2 times 6. 6 can be split up into 2 times 3. And then again, these numbers at the end of the at the end of the branches of this tree diagram, that makes up your prime factorization, which we can put together like that. So you've got 3 factors of 2, 2 factors of 3, and then 1 factor of 7. So even though the previous way I showed you, where it was very unbalanced, is technically right, it's making a bit more work for yourself. It can be a little bit more messy, more likely to make mistakes. So if you can do it this way, great. But the other way would still work. So let's see how we can use this prime factorization. Like, what is this even useful for? One thing it's useful for is finding what's known as the highest common factor. So we've already looked at what a factor is. So the highest common factor is basically two or more numbers. The highest common factor of two or more numbers is the highest factor we can find of that is, well, a factor of all of those numbers. So it's basically a number that will divide all of the numbers that we're considering, and we want the highest one possible. Right, so we can construct all the factors of a number, yeah, and then find the highest common factor from their respective prime factorizations. And I'll show you how that works in a sec. And yeah, it has many uses, not just in mathematics, but also in things like synchronization, engineering, construction. And I'm going to show you one example here, like saying construction, like a visual example that help you understand like the use of a highest common factor. So say if we've got uh, two different sized tiles and we want to divide this up into small tiles that we want to lay down on some floor, and we want them to tessellate together well. When we look at geometry, we'll look more into tessellation, but it's basically when things will slot together nicely. But we also want to chop these up in a way where we're not going to have any wasted material. So we could cut it up like this into 30 by 30 centimeters. That will cut up the bigger tile nicely without any waste. But you see the other one is going to have these offcuts. And so maybe that one will cut into 20 by 20 instead. So you get, a nice even cut without any waste. But then you've got two tiles of two different sizes that might not necessarily fit together so well. Ideally, we want them to be cut into the same size tiles. So what can we do? In this case, we could use what's known as the highest common factor of these two dimensions, basically 40 and 60. And you find the highest common factor of 40 and 60, they're 20. And so we divide each one up into 20 by 20 tiles. And you can see each one of them can be divided up exactly without any waste. And they slot together very nicely without, any, like mismatch of tiles because they're all the same size. So that's one simple example of what we'd use the highest common factor for. So how do we work it out? So we work out from the prime factorization of numbers. So we have, say, the prime factorization of 630 here. And then from that, we can basically come up with any other factors we want by making different combinations. You've got 2 times 3, which is 6. 3 times 5 is 15. 2 times 3 times 5 would be 30. 5 times 7 is 35. So on. Like any combinations of these factors we've got, we could do we've got two factors of 3 there, don't forget. So we could do 3 times 3 times 5, which would be 45. That'd be another factor. You can make up all the factors of 630 from this. You can see the prime factorization almost like a recipe, like the building blocks that then make up all the factors of that number. And we can do the same thing for 504. So we get all these factors. And now we want to try and find what the highest one is. But this isn't an exhaustive list here. And for a lot of the time, especially when you're dealing with big numbers, you can't make a complete list because it would take forever. But you can see here we've got some common factors, like they're both divisible by 42, they're both divisible by 14, they're both divisible by 21. So we see the largest one there is 42, but is that the highest one? We can't know for sure from this. We need more of a rigorous method of working this out. And how we do that is, right, let's make a note of all the common prime numbers, or prime factors that they have and how many of them. So first of all, we look at twos. They each have one factor of 2. You see the 504 has 3 factors of 2, but 630 only has 1. So in common, they only have 1. Say with 3, they both have a factor of 3, but they both have 2 factors of 3. So we can put down 2 factors of 3 there, like 3, 3, or 3 squared, whatever. And then finally, you see they've got a factor of 7. They don't share a 5. Only the 630 has a 5, but they've both got one factor of 7. So here's all the common prime factors that they have. And, well, they're all just one power. There's no. Oh, no, wait, no, we do have a square. We've got the 3 squared. So it's basically 2 times 3 squared times 7. If we put all that together, this will then give us the maximum factor that they're both going to have. And we can see that by, if we break it down like this, 630 is 5 lots of 126. 504 is 4 lots of 126. And that is how you find the highest common factor. Because you think about it, if you include any other factor, like say if I put a 5 into that, then we know it wouldn't be a factor of 504 because 504 doesn't contain a 5. It doesn't have that in its like recipe. And so we know this is the highest one. We've included as much as we possibly can. And we can also tell that from, say here, where I've shown them both as a multiple of 126, you see the 5 and the 4 don't share any common factors. Where say if we used 42 before, 630 would be 15 lots of 42, 504 would be 12 lots of 42. And you look at 12 and 15, they do share a common factor of 3. And that's a clear sign there that what you have there is not the highest common factor. So we can be sure here that this is definitely right. So now let's look at the lowest common multiple. So this is, well, it's what it says on the tin. It's like we want the multiples. Each number is going to have their own multiples. And you go high enough, every number is going to share a multiple at some point, but we want the lowest one. So it's basically the lowest number that is a multiple of both or all of the numbers. Like we could consider more than two. We can construct some multiples of numbers and then find the lowest one from them by, again, using the prime factorizations. And again, this has many uses, not just in math. There's things like signal processing and astronomy. I'll give you an example again from astronomy, a really interesting example using the orbits of the moons of Jupiter. They have something what's known as a resonance, and you'll see every so often they line up at the top. For every one, that grey one goes round, the yellow one goes round twice, the red one goes round four times, and then they all line up. And this has some very interesting consequences. And this is something we like to study in astronomy. And if you take how long it takes for each one of them to go round Jupiter, and you find the lowest common multiple of those, what are known as orbital periods, that will then tell you how long you have to wait for them to all line up again. So that's one possible use of this, but it's got so many uses. Um, right. So again, we take our number 630 and we find all the multiples of that number. So we've got two lots of 630, three lots, four lots, five lots. And one thing to add is that these multiples, we can easily find the prime factorization of those multiples once we already know the prime factorization of 630. So say if we take that bottom one, 4,410, we can see the prime factorization will be this because it's basically 630 with an extra factor of 7. If you was looking at 3,780 there, you've got a factor of 6, and that 6 we'd have to break down into 2 times 3, so just be mindful of that. But you see how once you've got the prime factorization of one number, it's not too hard to then find the prime factorization of all of its multiples. And we can do the same thing with 504, all of its multiples, 2 times, 3 times, 4 times, and so on. And you see this one here, 2,520. Again, you can find its prime factorization easily because you've just got that extra factor of 5 in there. And in fact, you can see that is a common multiple. And in this case, it is the lowest common multiple because you look at any multiples beneath these two, there's not one they have in common. So this one we could find out just by looking at it like this, listing the multiples. But that's not something we can always do. Like say if I change this slightly, we find the lowest common multiple of 630 and 508 instead of 504, you'd see that that is actually going to be over 160,000. And if we break that down into the two numbers, it's going to be 254 lots of 630 or 315 lots of 508. So we'd have to write a list that is over 300 numbers long. We haven't got time to be doing that. There's got to be a faster way. Well, here's a more rigorous and quicker way of doing this. So once we've got the prime factorizations of each of the numbers, now we're not just listing the common ones, we want to list all the prime factors. So what we're doing this time is rather than taking the lowest power of each number, we're taking the maximum power. So here we've got 2, 3, 5, 7. So this is all our prime factors that we have across the two numbers. And we take the highest power of each. So we've got 2 cubed, 3 squared, 5, and then 7. So we're taking the highest power of each. And the reason why we do that, because then we can see if we multiply all these together, that does indeed come out to 2,520. But in that prime factorization, you can see that each of those numbers, 630 and 504, lie in there. Like say if I show you here, you can see the prime factorization of 630 with a couple extra factors of 2. And then for 504, we can see its prime factorization. It just has that extra factor of 5. And so, and again, you can see the 2 squared and the 5, don't share any common factors. So we can be certain this is correct. And we can even take this one step further by including a third number. Like I said, you could get more than 2. It's very similar. Again, we list out all our prime factors and we just need to go through it and we need to take the maximum power of each to ensure, okay, that each of these numbers are going to be included in this number that we're constructing here. So we're going to take 2 to the power 3, 3 to the power 2, 5 to the power 2, and then 7 and 11. And if you multiply all that up, it comes up to quite a large number. Like as you include more numbers, the lowest common multiple of those numbers is going to get bigger and bigger. So, but you can get asked something like this. And you can do a similar thing with highest common factor. If you have three numbers, you apply the same technique just across the three numbers instead of two. One final thing to take a look at is kind of doing things in reverse. Like this is a very common higher grade question. Is say if you're given this information, you're told there's two numbers, their highest common factor is 21 and the lowest common multiple of them is 210. What are the two numbers? Okay, well, how are we going to work that out? Well, first things first, let's break these things down into their prime factorization. That's always useful in these kinds of problems. And so the problem we've got is we've got two numbers. Say if I just label them A and B, and we're we're given this extra piece of information as well that A and B are both greater than 21. So you'll see why that's relevant in a minute. Now, first of all, we know they're both going to contain the factors 3 and 7 because the highest common factor is 3 and 7. So it's a common factor. They both need to have that factor. And so that tells us the 3 and 7 needs to appear in both numbers. But the two numbers cannot share any more factors because this is the highest common factor. If they both now had, say, a factor of 5, the highest common factor wouldn't be 21, it'd be 105. 21 times 5, basically. So that's what the highest common factor tells us here. They're both going to have factors of 3 and 7, and they can't share any more factors. Now, the lowest common multiple, that tells us that somewhere 2, 3, 5, and 7 need to appear. So, well, we already have 3 and 7, so we don't have to worry about those. It's the 2 and the 5. Now, they could both appear in one number, or they could appear in like one in each number, which would be ambiguous in and of itself. That's why we've been given this extra piece of information, telling us that both numbers are greater than 21. And 3 times 7 is 21, isn't it? So that tells us that each one needs to have another factor each. So the 2 goes with one number and the 5 goes with the other. And so there we go. From that information, we've managed to, we can see that this prime factorizations would produce this highest common factor and this lowest common multiple. And so we calculate that out, it comes out to 42 and 105. That's about as tough as it can get on these kind of problems, which really tests how well do you understand these factors, multiples, highest common factor, lowest common multiple. Right, let's leave it there. So let me leave you with a did you know? Like, did you know there are organizations actually offering cash prizes for finding new, very large prime numbers? And the reason why that is because they are super useful when it comes to fields like cryptography, which allows us to message each other safely. Like you might have seen, say, on WhatsApp or something, and it will say end-to-end encryption. Encryption, that's basically cryptography. It keeps your messages safe that no one else could read them when you send it from you to someone else. The largest known prime number was actually found very, very recently, in just November 2024, and it was found by an amateur mathematician, which has over 41 million digits, a really big number, and it actually can be represented like this. This is what's known as a Mersenne number, a number that's basically one less than the power of two. But you see, this is 2 to the power 136 million, and so really, really big number. And yeah, the cash prize that they offer, there's what 150,000 award for finding one that's over 100 million digits. So we're only at 41 so far. 100 million digits gets you that, 250,000 for over 1 billion digits. So yeah, if you ever find one of these very large primes, you'll be a wealthy person. So here are your takeaways for today. Make sure you understand like the checklist, everything that you haven't left anything out because this is it now for numbers. So maybe you want to go back over the past videos, make sure you've got everything well understood because we'll be using that in the future sections, especially in our next section on ratio and proportionality, where we're certainly going to be using a lot of our work we've done on proportions, decimals, fractions, percentages, that sort of thing. So I will see you there.